I was just talking with Leon. I don't know if someone has seen Leon yesterday here. Gave an amazing talk. We were talking about we're talking about KCD that's coming. We're talking about Pesach, and we started talking about cleaning, you know, and what people will do to avoid cleaning. Who likes to clean here? Nobody. Oh, you do? Great. I'll invite you. So, people don't usually like to clean. We'll try to avoid cleaning and tidying things around the house as much as possible. We're going to talk here today about technical debt, and we'll see how it relates a little bit to cleaning and the consequences as well of not cleaning or not tidying up enough. So first, we'll talk about technical debt, what it is. I won't get into too much detail. This is not a theoretical talk about technical debt. This is more like practical examples of how you can limit technical debt. Then we'll talk about the importance of standards and stability to avoid and limit technical debt in your stack. Then we'll talk about loose coupling and how loose coupling can help you, how spreading the technical debt can help you limit, and how immutability has a role to play in this as well. We talked about debt dilution and delegation. This will be especially important in the context of DevOps days and the human side of things. Then speed versus haste. That's the whole idea of the tortoise and the hare. Should you try to go fast, or should you try to have a good, steady rhythm? And then finally, an example of betting on the right horse. What are the kind of ideas you can get from the points we'll see to choose the technology that will help you limit technical debt on the middle to long term. So I'm Raphael Pinson. I'm a solutions architect working at Isovalent, working on Cilium, Hubble, so networking, security, and Kubernetes. If you're interested at the end, you can come. I have stickers, I have books. So don't hesitate at the end. And today, let's talk about technical debt. So what is technical debt? Technical debt is something that creeps in your stack by making a lot of small decisions, postponing decisions to update software, to keep your stack up to date, to change that library in your stack, and eventually you come to a point where you need to provide a lot of effort to make a small change. So that's how it's kind of similar to cleaning, right? Because if I don't clean at home, and I usually don't like to, there comes a time when I need to invite someone in my home, and then all of a sudden, on top of preparing the food and making sure that they feel welcome, I need to clean, I need to tidy, I need to mow the lawn, I need to do everything, and that's a lot of work because I've accumulated a debt. So this idea of a debt is that there is something to pay at some point, which is more effort or more money than should happen if I only had to do, let's say, prepare a meal to invite my friend. Technical debt is hard to monitor. It's hard to monitor because it's a lot of small decisions. It creeps in, and it can go unnoticed for a long time. And usually you realize that you have technical debt when it's time to pay. So you might only realize it, when you have to update a component because you need a new feature. That's actually the best situation. You're like, I need this new feature, but actually I need to change this library. And actually, in order to change this library, I need a new OS, and I need a new virtualization system because the new OS needs, whatever, you need to change the whole stack, and it's going to take 6 months, right? And that's the best situation because that's just for a new feature. The worst situation is there's a security problem. It needs to be fixed yesterday, and I just found out it's going to take a year because I need to change the whole stack to fix the system. So usually you find out when it's time to pay, and it looks something like this, right? At some point in time, you had a system that was up to date with the state of the art. And then the state of the art kept evolving, and your system got stuck. It's usually not entirely stuck, right? You get minor updates. Maybe you change your configuration. Maybe you're bringing some patches here and there. But you're getting increasingly further away from what is now the state of the art. And the cost of change to get back to the state of the art, to the standards, gets increasingly expensive. And you don't need all this stuff. You don't need the state of the art for a long time. And then all of a sudden, you need the state of the art because there's a feature that you actually need, because there's a security patch that you actually need. And this is what you're going to pay to get back to it. So you can see that it has a lot to do with standards, right? State of the art is about standards, about what people agree is the way to do things at a certain point in time. So let's talk a bit more about standards. Standards is interesting because everyone has a different way of looking at it and a different way of thinking, what are the standards I'm willing to accept, right? In a lot of teams I've talked to over the years, and a lot of DevOps or operations slash CI/CD slash cloud automation teams that I've talked to over the years, they usually have a limit to what they're willing to implement, which is what they know how to implement. Let's take an example of, let's say, a Terraform module, for example. Let's say I need to automate a VPC on AWS, and I want to write a Terraform module. Chances are, in a lot of teams, you will say, I know how to write Terraform code. I know how to write Terraform DSL. It's not too hard. 10 lines of code, I can automate this thing with the Terraform provider. So why would I use a module from the community that is actually much longer, has tons of parameters? I need to understand how it works. I need to read the documentation, make sure it works and so on. I'm just going to write my own. Okay, you decide to write your own. And the problem is, at some point, you're going to need a feature that is in the official module that is too complex to implement yourself, and you're stuck with this module. So very often in teams, the problem is, if I know how to do it, I will do it. Imagine now if you had a kernel developer in your team and they decided that they would recode the entire operating system because they can do it, right? That's usually not the right approach. So you need to decide what is the right abstraction. Where are you going to rely on standards and where are you going to do it yourself? And usually the right answer is not, if I can do it, I will do it. That actually is an answer that usually drives you towards technical debt. But there's another problem that can happen. So in September last year, a year ago, in a previous life, I was in another company, and we were at a summit with this company, actually. And there was this bug. I don't know if not a bug. Someone remembers there was an expiration of the root CA X3 certificate. You remember this? This was a root certificate that was used by Let's Encrypt in the early days of Let's Encrypt, before Let's Encrypt had its own root certificate that was accepted by everyone, which happened somewhere around 2016, right? So before 2016, Let's Encrypt certificates were signed only by this root certificate, and then the new root certificate from Let's Encrypt was accepted by everyone. For years, until September 2021, the certificates provided by Let's Encrypt were signed by both root CAs, so they would be accepted on both old systems and new systems. And then September 2021, this old certificate expired, so, fine. For anyone that had an OS newer than 2016, you were perfectly fine, didn't see a difference. Your certificates were signed by something that was trusted since 2016, fine. If you had an OS that was older, that was another issue. We looked at our OSs, we're using OSs that are much newer than 2016, we're fine, everything's fine, right? Except everything broke. And it happened in the middle of the night, and we were at a summit, and it wasn't fun. We spent the whole night fixing it. And what was the reason? We used Rancher 1.6, which is an amazing platform. And Rancher 1.6 was something we were in the process of migrating to Kubernetes. We knew that we had to migrate, that Rancher 1.6 was not supported. The OSs we were running on the nodes were new enough, but the containers that were running the services for Rancher 1.6 ran on Ubuntu 16.04. So the containers that ran the services, the metadata services and the servers and things like this for Rancher, actually didn't know about the new CA certificate, and we were using Let's Encrypt for communication between the Rancher components. Game over. So we were actually following standards. We're using Let's Encrypt, we're using Rancher, we're using Docker, all standard stuff. But we were lagging behind in terms of standards, and we got bitten again by technical debt, and it took us a lot of effort to actually get back on track with this platform. So again, this is one thing to keep in mind. Even when you're following standards, you need to make sure that you're following up-to-date standards and make sure that you know when the standard is going to expire and you move fast enough to catch up. So there's actually a strong link between standard and open source, especially in our time, right? 20 years ago, open source was a thing of its own. Nowadays, if you want a new standard in terms of networking, in terms of deployment and so on, you usually need to think about it in terms of open source. So let's face it, right? I talked a bit before about not invented here syndrome. Let's make my own thing. Let's make my own Terraform module. Let's face it, we all have very similar needs, right? We're all using computers to do pretty much the same things. So chances are, if I need something, you probably need the same thing. And if you don't need it right now, maybe you'll need it next week, right? Or else, maybe I'm not understanding exactly what I want to do. So let's consider this Terraform module to automate a VPC, for example. this is a standard. I'm using the standard module from the community, what pretty much everyone is using, and I have a new need. So what should I ask myself to make sure that I stay up to date with standards? Well, first question is there already a way to do this? Is there already a new version of that module that actually provides my new need, this new parameter I need? Is there, if that doesn't exist, maybe there's a fork that provides it. Is that a good idea? I should ask myself. If there's a fork, is there maybe a pull request that is open that provides this need? I could use the pull request, or I could try to push the community to accept the pull request so that I stay on a new version of the standard. If there's no pull request, maybe someone has a fork and I can find it, talk to this person so that they open a pull request, right? If all of this fails and there's no way to implement this in an existing way, is my need actually valid? This is a question that is important to ask yourself, right? If nobody else has provided a solution, you should ask yourself, do I understand the problem? Because again, we're all trying to do the same thing. So do I actually understand what I'm trying to do? Talk about it with other people in the community, in your team. Maybe you'll realize that you're not looking at the problem the right way. And if you look at it another way, there is already a solution that exists for your problem if you just think of it another way. Okay, let's consider that you've talked about it. People are saying this is a valid need. It doesn't exist yet. There's no solution using your tools. This is a valid thing. You need a new parameter in this module. Nobody has done it yet. You're the first one. Great. Implement it. Fine. And now you're thinking, okay, yes, but I'm not paid to do open source, right? This is not my thing. If I implement it, I don't see why I would give it to the community. This is not, it's not the Red Cross or something like this, right? So I'm going to keep it for myself. I'll just implement it on my side and, fine. And I'll wait. If you do this, what's going to happen is that chances are in a week, in 2 weeks, in a month, someone else will have the same need. They probably do already. And they will implement it. And one of them will provide it back to the community, to the module. And then what happens is that this implementation will become the standard. And chances are it will be slightly different from your implementation. The implementation itself doesn't really matter. The interface matters. The API matters, right? So maybe the parameter will have a different name. Maybe it will have even a different structure. And you'll have to migrate to that new standard. So what you've done by implementing it only for yourself and not bringing it back to the community is you've actually built technical debt on your side. On the other hand, if you decide instead of following standards to influence the standards, and I'm not talking about big standards, right? I'm not talking about redefining RFCs or whatever. I'm talking about small standards, parameter in the Terraform module. If you decide instead to influence the standard, then you can actually stay ahead of the curve because you're saying, hey, here's this new standard. Someone has this need for a new parameter. Here it is. Get it merged in the module. Anyone can use it, and you're actually ahead. And you get to set a new standard, which is pretty cool. Even if it's a small standard, you're actually the one defining it. So this is one point that is important when it comes to standards and the importance of open source and defining standards and limiting your technical debt. Now let's talk about loose coupling. About 15 years ago, I was big into contributing into Ubuntu, and I used KDE at the time. That's before they switched everything to using MySQL for calendar, and it got really complex. Anyway, we're not here to talk about KDE. And so I was contributing to Kubuntu. And about 10 days from release, I realized that I could not print on Kubuntu. It just didn't work. It worked the day before, it didn't work that day. I'm like, okay, something went really wrong. So I looked at the changes, and cups had just been updated. So the cups system to print to a beta version. I'm like, who updates cups to a beta version 10 days from release date? Doesn't make sense, right? Who did it? So I checked who did it. We can trace it. And it was a GNOME developer, obviously, right? So as you might know, the whole idea behind Ubuntu from the beginning was that it gets released on the same day as GNOME, so that you get the latest version of GNOME. And so everybody wanted to use it in the beginning of Ubuntu. That was the idea, because you get the latest features from GNOME on the day that it gets released. And I said, why did you do this? Why did you add that cups to a beta version 10 days from release? They said, because the new version of GNOME actually needs that cups version. And I'm like, yeah, but the current version of KDE actually doesn't work with that cups version. What do we do? We're 10 days from release. So we actually got it fixed, right? But this is a great example of hard coupling, of a monolith kind of system. And if you're familiar with Linux and shared libraries, you know, there's great blessings in shared libraries, right? It reduces a lot of weight of the system, but it also brings a lot of issues as well. Yeah, I need to update this library to get my new camera to work, and all of a sudden I can't use my webcam anymore, right? Because everything is strongly coupled, and libraries are very strongly coupled in the system. So monolithic systems are strongly coupled by design, and they're hard to update. And the result of this is the technical depth of these systems is also strongly coupled. You change one library at the bottom, you can impact anything in the stack. Usually in a system like Linux, you can track it through dependencies with packages, but even then, try to take a basic library in Linux. There's a tool, you know, using apt-get, there's a tool to actually generate a graph of all the dependencies that are impacted. This is very scary. I don't think anyone comprehends really the impact of changing a library at the bottom of the system. So we need to actually have loose coupling.
Okay, you're in bed. She's over on your side, cuddling. Now, you wait for her to drift off, and then you hug her and roll her over to her side of the bed. And then you roll away. Hug for her, roll for you.
All right. So what we need is actually a way to separate the components so that they have less dependencies. They have their own space so that they can manage their own depths. So that's the idea of a microservices approach. That's the idea behind containers as well. It's the idea that each service, each workload will bring its own set of dependencies and they won't be shared. So all of a sudden, if I have my two workloads, service A and service B, they actually use the same library. If they were on the same system on a VM, updating this library would impact both. But if I use containers, for example, or even virtual environments, then all of a sudden each of them comes with a copy and they can update the library to different versions and they're free to actually do so. So I have decoupled my system, and this has a great impact on technical depth. So it's a decorrelation of dependencies and it distributes the technical depth horizontally. So how do we fight strong coupling? Well, I've just mentioned a little bit containers, right? I'd like to get back on where this came from and the whole idea and how it's linked to immutability, right? So let's get down to what is immutable system. So if we look, historically, we used to have physical machines and deploy OSs on them, deploy libraries, middlewares, software on top. Then we moved to VMs. Now we're moving to containers. And an immutable system, typically, this is a system that evolves with time. And we've made tools for like configuration management, such as Puppet, Chef, Ansible, and so on, to try to keep the drift from getting out of control. So we have converging tools that will once in a while bring back the system into its target state. This is fine, but it's actually in a lot of cases not ideal. And immutable systems, immutable infrastructure came up to solve the problem of not exactly knowing in which state you are at a given point, with the idea that instead you should replace the entire system every time you make a change. So it's the idea that, okay, let's say my trash is full, I'm just going to get a new house. This is extreme, right? Because this is physical stuff. And it's still extreme when you think of physical servers. If I need to change the DNS resolver configuration on my server, I should change the server. On a physical server, this is crazy. You don't do this. It will take 2 weeks, and it's not doable. With VMs, this is starting to make sense, right? So the idea that you get a full replacement of your state is doable with VMs using an approach of golden images. Typically, you make an image using a tool like HashiCorp Packer, for example, or something similar. And then whenever you want to change something like a DNS entry, a DNS resolver entry, you just update the thing, update the new VMs. There was a great blog post a few years ago about this, about the different approaches. Remember, Mark Burgess, the creator of CF Engine, was all in favor of mutable systems and convergence, or even concurrence if you can do it, using systems like MGMT. There was, Michio Hashimoto, the creator of HashiCorp, that pretty much said, do whatever you please. There was another guy, I don't remember his name, sorry, who said, no, immutable is better. We just have, backend and frontend kind of machines. We deploy them on tons of VMs on AWS. And whenever we want to change anything, we just make a new image, deploy the new instances, change the load balancer, remove the old images, the old machines, and we're fine. That works great if you have 2 images, if you have 4, 5 images, maybe. In a lot of situations, in enterprise situations, you have 600 images, 1,000 images, because there's tons of combinations of OS plus middleware plus software plus configuration plus who's allowed to access it and so on and so forth. And it becomes totally unmanageable to create the images and roll them out. Fortunately, what we've done, if we started actually, this is not yet here, we've started actually rolling out from VMs to containers. And containers actually move the level of immutability from the VM, from the OS, to the containers level, which is the application. So there's a decorrelation, vertical decorrelation between the container, the application that runs in the container, and the OS it runs on. So all of a sudden, you don't care about the OS it's running on, so long as it has a container runtime that it can run. And this is great, because it means that now you can deploy this immutable artifacts on pretty much any system, and that frees you from the problem of having to maintain tons of combinations of OS plus middleware plus application. You just need to maintain your small components, which are essentially usually microservices implementations. So this allows to distribute the technical debt both horizontally and vertically. Horizontally, as we talked about before, in an approach of loose coupling, splitting your monolith into different blocks that can evolve separately, and vertically as well, because as you add layers to the platform, you will distribute the debt to the platform. Because in the past, when you needed to upgrade the OS, the operation team had to talk to developers and say, we're going to update from Ubuntu, let's say 2004 to 2204. Are you okay with this? And they would have to look at the libraries that came with Ubuntu 2204 and say, oh, wait a minute, there's this new library, we need to rewrite the software because now there's a new version of Node that comes with the system and this is horrible and it's going to take us a year to migrate to a new version of Ubuntu. But now with containers, we can say, whatever, you provide a Docker or a container D or whatever, you provide a container runtime, I'm fine. I have my images, I have my containers, I'm responsible for what's in there. Which means that operations are now responsible for the technical debt of the platform, and developers are responsible for the technical debt of what's inside the containers. You can add layers. You add Kubernetes. There's the technical debt that is linked to Kubernetes itself, and the APIs that are provided are loosely coupled. They are long-running. They are stable, these APIs, more or less stable, right? If you're Kubernetes, there's some deprecation, but they're more or less stable compared to the deprecation timing lifecycle of the OS beneath, right? So, and as we're going forward, going from VMs to containers to functions as a service, and we're more and more decoupling both horizontally in terms of splitting the workloads and vertically in terms of adding layers in the platform that allow for specific management of the debt. Public cloud is actually a great example of this. If you think about it, very often we think of public cloud like I'm paying someone to run the machines. This is true, but you're also and mainly paying people to take care of the technical debt for you. When you're running an AWS instance, you're actually paying AWS to take care of the whole technical debt of the infrastructure, the VMs, maybe even the OS if you have a managed service. All this thing is taken care of and is being updated for you as far as new versions and security by the AWS team. This is what you're paying for. But be careful because this is one way to reduce debt, or at least the ownership, right? It's not your debt anymore, it's someone else's, you're paying for it. But there's still a way to build a huge debt on this if you rely on specific features of this cloud. This is a different kind of debt. This is a debt that is linked to the fact that if you rely on specific features of AWS, you lock yourself with this provider and you won't be able to switch to another provider. So whenever you have a need that is specific to another provider, you will need to spend a lot of effort, energy, maybe money to switch to that other provider because you've locked yourself. This is another type of debt you have to be careful. So one principle of DevOps that applies here is don't look for the local optimum, which might be, let's use this memcached service on AWS because it's all ready and available, but look for the global approach in a DevOps approach, which is look for the global debt. What is it going to cost to switch to another service that doesn't exist on Azure if you need to migrate to Azure? I'm not saying you need to go to Azure, right? It's just an example. All right, so this brings us to the idea of depth, not only depth distribution, but depth dilution and delegation, which is a very important point because this is DevOps days. We talk about people. We are people after all. So let's talk about Conway's law. Conway's law is a law that was enacted in the 1960s that says that the architecture of your software will reflect the organizations of your teams, whether you want it or not. So if you have a team that is all in one room and everybody can talk to each other however they want, you'll get a monolith. And there's no way to escape this. If you want to escape this, if you want microservices, if you want loose coupling between your components, you need to make it so that your teams will communicate in a way that models this architecture, in a way that their communication is a reflection of the architecture that you want. So the consequence of this as well is that as you split your components and as you organize your teams in such a way that they reflect this architecture, you will actually split and dilute the depth ownership. Why? Because every team will only be responsible for the depth of their own component. And if you think about it, you get a monolith. In a monolith, most people cannot understand what the depth is and how to manage it. You change anything at the bottom again, you can have huge repercussions. But once you start splitting, every team can understand the technical depth of their own component. And if there is loose coupling between the components, they can be updated separately, which means you can actually manage the depth of the whole system. Why is this important? Because, and I recommend reading Team Topologies, an excellent book on the subject, because we are humans, and there's an amount of energy and mental load that we can have, and we cannot go beyond this. And the mental load of the team is something to consider as well. So can your team actually manage the technical depth, the complexity of the technical depth of their component? If they can't, you need to consider actually splitting the responsibilities so that they're able to tackle the technical depth of the component they're responsible for. This brings us to speed over haste. In a lot of companies, when they want to tackle technical debt, when they're like, we need to update to the new system, they'll make a plan. In 1 year, we'll be there. We're going to update this system and all the dependencies and this and that. This is the big plan. We'll be there in 1 year. Chances are it won't be 1 year and we'll be maybe 2. And then even if you make it in 1 year, you'll be 1 year late because the specifications are from today. And they might be updated a little bit, but chances are in 1 year, you won't be up to date with the state of the art. You'll be late. So this is the rabbit, the hare kind of approach, right? I can be fast, so I'll make big jumps. On the other hand, you've got the tortoise approach. The tortoise approach is, I can't make big jumps. I can't do this. I know it's impossible. I'll always be late. So let's just be steady. Let's go slowly. Spread the load. Give it to different teams. Let each team manage their components so that the component stays up to date. They can do it because the load and the mental load and the technical depth is manageable per component. And then as it goes, the only thing that's left is updating the architecture, right, which is still a big project, but the global technical depth can be distributed and diluted between the teams so that you can stay up to date. It's not about going fast. It's about being steady. How does this relate to the 3 ways of DevOps? Because, I mean, this is DevOps days after all, right? The first way of DevOps is flow and system thinking, from developer to operations. Well, if you decouple your software architecture from the infrastructure, then you lower the risk of technical debt. If you use containers, for example, and you do it well, chances are your operations won't have to ask developers, is this okay if I update the OS? No, they know it's okay, right? They're providing an abstraction that makes it so that they're responsible for the debt, the developers are responsible for the debt, and the operations can actually change things if developers have done this properly to decouple themselves from operations. Amplified feedback loops is the fact that operations need to get back to development or even ideally get involved in the architecture itself. Well, development, they know a lot of things, but sometimes they don't know that this interface that is available in the infrastructure is not a good idea. It's too strongly coupled. There might be an alternative that is loosely coupled, more loosely coupled. If they ask operations, if operations is involved, they can say, use this abstraction instead. This abstraction is long-standing and it's more stable. We might change the implementation, but this abstraction will stay. And if you implement it this way, you won't need to refactor later on, so you won't build technical debt. This is one way that it can happen. In general, operations can help design the software in a way that it will be less coupled with the platform so that you don't accumulate technical debt on the platform. Finally, culture of continual experimentation and learning. I think this speaks for itself. This looks clearly more like a turtle than a hare. This is going slowly in the right direction, reevaluating your direction as you go instead of trying to make big jumps, which doesn't work. So finally, once you know all this, how do you choose which technology to go into? You know, I'm working for Isovalent, we make Cilium, so there'll be my shameless plug into a bit of what we do as an example of how to reduce technical debt using technology that is both loosely coupled and standard. So we've seen, well, let's talk a bit about this. What is the right time to adopt, right? Usually a lot of companies will think, well, let's go to late majority, right? Let's wait until it's extremely stable. The problem with this is that this will mean bigger jumps from one technology to the next. So if you want to have this approach of continuous experimentation and learning, usually you need to be in the early majority, if not in the early adopters, so that you can actually keep up to date with the state of the art instead of trying to fix new problems with old technology all the time by making big jumps. And in the meanwhile, fixing however you can. So we've seen two criteria here. Again, this is by no means a complete way of understanding and seeing technical debt. It's just two ways of looking at it and reducing it or trying to limit it. We've seen stability. Stability is important. So the more stable the interface is, the least you will have to refactor your interfaces and rework the way you interface with them. Oops, what did I do? There you go. So standard interfaces is important. That requires few changes in time. And the second thing is loose coupling, which can allow for partial upgrades, splitting your load, delegation of tech debt, dilution of tech debt between your teams, and eventually just having configuration changes to manage how the components talk to each other. So let's talk about one technology that actually meets these two criteria. I'm going to talk about eBPF very quickly. I could spend an hour talking about eBPF or more, but just very quickly. Does anyone know what eBPF is about? Yes, a few people. So chances are you've already used eBPF. Let's say if you have an Android phone, for example, and you look at how much bandwidth your applications are using, you're using eBPF, because that's the only way in the Linux kernel to know which application is using the network, unless you have a proxy, is using eBPF. Facebook uses eBPF, Netflix uses eBPF, tons of people use eBPF now. What is it? It's a way to extend the kernel dynamically without recompiling, without even rebooting. It extends the Linux kernel. Now, even Microsoft actually is porting it for Windows. So eBPF has both stability, because it's based on the Linux kernel. This is kind of the most stable thing you have in your OS, right? Can't think of something more stable than the kernel. And it's loosely coupled. Why? Because you can extend the Linux kernel to add observability, where's my list? Observability, security, networking, tracing, and profiling. All these things can be added directly at the kernel level in a way that is totally transparent for the applications. The applications don't even know this is being done. For example, in terms of networking, you can implement network policies, you can implement more efficient routing, you can implement even features that don't exist in the Linux kernel, such as SRv6, segment routing for IPv6, or big TCP, things like this, by actually bypassing stacks of the kernel and rewriting them in eBPF. It's totally transparent for the applications. So just a bit on eBPF. eBPF here is used by a lot of applications. Some examples are BCC, Cilium, Falco, Katrin, BPF Trace, and most of them rely on SDKs. So there's SDKs for lots of different languages. Most of them rely on the Go SDK. And what happens is that these programs will generate BPF programs written in C, in a subset of C, that get compiled to bytecode. And then these bytecode programs get injected in the kernel. And what's very special about BPF compared to writing a kernel module, for example, is that this bytecode will be verified by the kernel before it can be accepted. And once it's verified, it's accepted, and it can be run and attached to events to implement observability, networking, security, and more. If you have questions, you can come afterwards, because I don't have much time to finish explaining. Some examples. Cilium allows for performance gain, or even simpler architecture in Kubernetes by implementing networking using eBPF. Hubble allows for fine-grained, low-latency observability in the stack using eBPF. And Tetragon allows for observability and security enforcement on the nodes using eBPF. It can even block processes from executing in real time, because it can say, hey, you know, this process is trying to escape C group, for example. Let's kill it. So if you have more questions about eBPF, you can look at, we have an Echo podcast that streams every week, every Friday, either European time or American time. There is a newsletter that comes out every 2 weeks. And there is a Cilium and eBPF Slack server. There's much more. There's labs if you want to have some links for interactive labs. So if there's a conclusion here, what matters is not the speed, it's the direction, right? You can try to go as fast as possible. This won't help you to reduce your technical debt. What matters is look at the right direction in a spirit of continual experimentation and learning. Split the load, dilute the technical debt between your teams, and make sure that everyone is able to manage the technical debt of the components so that the whole of the system can be managed. Thank you. This is it for me. Any questions? Yes?
Maybe something like, do you see that the evolution of microservices can create a new level of technical debt? I don't know, which maybe people don't think first.
Yeah.
Too many microservices, for example.
Yeah, so this would be a big subject, but this is a difference between a complicated system and a complex system, right? Monoliths are complicated. They cannot be comprehended in a lot of ways. Complex systems have their own complexity, right? It's not easy to manage, but they can be comprehended much better because the system is split into several. Yeah, but I agree. I mean, there's new ways of building technical debt, but at least I feel like this technical debt that is spread can be actually understood at the level of each microservice versus the monolith that is totally incomprehensible.
Is it a problem when using eBPF and its features that like people are blindsided by that eBPF is used in some way? Like, yeah, people don't know about it, and it takes some part of setup, and
That's a good question. I think in a lot of ways, you think of implementing networking on Kubernetes, you usually don't think of the underlying IP table rules that are being written. And good for you, because you don't want to look at how it looks because it's horrible. And in the same way, if this is replaced by eBPF programs instead, it's still transparent to you what happens in the kernel. Most people don't think about it, actually. But yeah, it's true in some ways. Some things can happen that are a bit magic. You can go all the way to actually offloading some things. In the same way that GPU is allowed to offload graphics, you can offload like networking code to specific network cards, devices that support it, and the kernel won't even see it. It's all a balance between what you want to observe and the performance you get. If you have more questions, I have stickers, I have books as well if you want. So thank you very much, and have a good end of the day.